Hi, welcome to online tutorial series on digital signal processing using MATLAB and Python. So as we know, as we have discussed in introductory video, in this tutorial series we will be talking about some of the basics of DSPs and how to implement some of the programs using Python and MATLAB. So let's start. So this is the first lesson, and in this we will talk about signals, what are digital signals, and how to represent these digital signals in digital domain. Okay, so let's start. So first thing should come into my mind, like what are the signals? So signals are nothing but information carrier. So we can say anything which carries the information or which carries the data or which carries the information is signal. So this is a very crude definition, and where is the simplest one? So the examples could be like audio signal or the speech signal. We can say audio signal, speech, etc. So particular we talk about this audio signal, speech signal, these are known as the one-dimensional signals. That means they depend only on the time. These are all the function of time only. Another dimension of the signals could be like images, or could be X-ray images or any pictures. These are also a kind of signals, and generally these are called the two-dimensional signals. Why? Because the value information at any point depends on this X location and the Y location. Only then we can say it is a picture. Similarly, if there could be some other four-dimensional of signals as well, like temperature location or wind data of any geographical location. So in this, the wind data depends on the latitude, longitude, temperature, and the time. So all these are the various kind of signals. So if someone say like what is a signal, so its simplest form, like it is a function of something. So the representation is, if we say how we represent a signal, so we can say it represents like x of t. So it is representing a function of time. So it is a complete representation of the signal. Similarly, if we talk about our images, so we can say images x comma y, where x and y the coordinates. So the intensity vary x comma y. So these are the kind of representation of any signal. So we can also represent these signals with the mathematical descriptions, like if we have proper mathematical description for say x of t is varying with respect to say t square plus 4t plus 1. So this is a signal which is varying with respect to time by the following equation. Similarly, we can also write like x of t equals to sine omega t. So in this case it is a sinusoidal signal in which it is varying with respect to time with the sinusoidal fashion. Okay, so we have done about signals. Now the things come, what are the various kinds of the signals, right? So we can say the types of the signals from the representation domain. In terms of the representation domain, if we talk about, so we can say type of the signals basically into two categories, broadly classifying like analog signal and the digital ones. So these analog signals can be further classified into two parts, and those can be continuous time signal So in this analog signal, the amplitude uh, can have any value between minus infinity to infinity. So based on the time axis, this can be divided into two parts, like continuous time signals, and we can have discrete time signals. And similarly, the digital signals, if we talk about, so digital signals, as the name suggests, they can have only values like 1, 0, 0, 1 only. So only two signals like 1, 0, 1, 0, 0, 1, and so on. That is time, and this is the amplitude. So these are the very interesting things, like continuous time signal. So continuous time signal means for every instant of time we have some value of the amplitude. For say like this is the time, and this is like x of t. Okay, so now we are moving forward towards the digital signals and to representation digital signal, and we will be discussing some of the briefs which comes into those part into between. So when we talk this continuous time signal, they exist at every instant of time. So you can say what is the value at 1 second, you will find okay, this one is there. What is the value at 1.1 second, you will find some value. What is the value 1.111 second, obviously you will find something. So on. That means there are infinite number of possibilities in continuous time signal. So infinite number of possibilities means there could be infinite numbers of time points on which you can query, like what is the value of signal at those possible time. And similarly, there could be infinite number of possibilities of having the amplitude, because it will have at every instant of time. Now and all real life signals are analog in nature, like whether we talk about a speech signal, whether we talk about temperature signals and everything, because they exist at every instant of time. Signals are continuous time in nature. So obviously when we talking about introduction of computers, or if we discuss the problems with this continuous time signals, there's a major problem. We can't store all this information because we have a limited memory. So it is obvious that we can't store the infinite number of possibilities inside a computer, and all the computer based are the memory devices. It works on certain memory, that means on the storage. So what we do, instead of having this kind of signal, we have some other signal representation, that is a discrete time signal. So what we do, instead of this time information which is infinite possibilities, so we know the signal doesn't change very fast if we talk about a real life signal. So if we have 1 millisecond, if we have some information at 1 millisecond of time, so it is possible the information would be similar at 1.1 millisecond. So that's why instead of storing all the information available in the continuous time signal, we discretize the time domain. Or another example is we sampled out the time domain. That means instead of defining the signal like this, we define the signal at specific instants only. For say 0 and say 1, 2, 3, 4, 5, 6 and 7, only the at integer instant. And when we say these are the integer instant and we are converting into time, so whether it could be 1 second, it could be 1 millisecond, or this one could be representation of 1 microsecond. The only thing that depends like on what is the scale of this in terms of second, that depends on the sampling period. Depends on the sampling period t. So if the sampling period is in microseconds, so this will be 1 microsecond, 2 microsecond, 3 microsecond. And similarly we can define the sampling period, the time gap between these two. So this is the sampling period time. Now this was the original signal, and now we are defining it, so it would be like this one. So this would be the another kind of representation of the signal. So instead of having all the information, we are having information of the signal on at a specific instance, and there is no information in between these two, right? So in between these two it is a void, there is no information. Okay, so generally in books you may find such kind of representation. So still it comes into the analog category because the amplitude is still can have any values. It could be 1.1 or it could be 1 point or say 2.5, 2.6, and any value could have. But at time axis we have discretized it. That means they can have any specific number only. So now we represent these as nt, yeah, or x of n. Right, so these are the discrete time signals, and now coming to the digital signals. So as we discussed, digital signals are very specific in nature. So here we have discretized it into time axis, or quantized. There is no information between these two. Similarly, if we quantized or discretized on amplitude axis, then that becomes a digital signal. And a representation of digital signal is the coding that we'll talk about later. So like this one, we have defined only the labels like 1, 2, 3, 4, and so on. So digital, this is the digital signal. So these two kind of signals are very common or are very near to each other, and generally used, notation is used interchangeably for both of the things. The only difference is the representation. This kind of discrete signal is the representation when we'll be dealing with computation, and this kind of notation we use when we're dealing with the from the computer point of view. Okay, so these are the basically two kind of signals, and in DSP we will be dealing with discrete time signals or digital signal. More or less both are the same, and you will understand why these two things are same. So when we talk about how to convert this analog signal into a digital signal, because prior to understanding the digital signal processing we need to understand the basics. So how to convert analog signal to digital. So generally there is a simple phenomena. You will say okay, A to D is used, but there are several things which happens inside the A to D, that means analog to digital converter. So first we have a sampler, and then we have a quantizer, and then we have a coder. So this is the entire this entire block diagram represents the A to D conversion or analog to digital conversion. Right, now let's think about it. Let's go into the detail. When we talk about a sampler, so this one, now the output of the sampler, let's represent it here, output of sampler. So output of the sampler would be like this, because it is a kind of, we are converting the signal into discrete domain. So we have some sampling frequency, and based on that it is taking out some samples, say 1 second, 2 second, 2, 3, 4th instant, 5th instant, 6th instant, 7th instant, and 8th instant, and so on. So it is a sample number, and now it represents like NT. So as I said, these are the numbers, and if I say whether it is a microsecond or millisecond, that depends on the sampling frequency. So here we come to the concept of the sampling frequency. Let's say we are sampling frequency of 1 millisecond. That means this represents 1 millisecond instant, this represents 2 millisecond instant, this represents 3 millisecond instant, and so on. So simple, generally it is represented as NT when we convert the signal, or more or less for easy configuration we represent N and define separately, okay, what is the T. Now this T is the sampling period, or generally also known can be represented as in terms of the frequency. So this is Fs, where Fs is the sampling frequency. Now there is a quite relation, or there is a one theorem which relates these two things, and we'll not go into the detail of that because we are not covering in this lecture. That is the sampling theorem. We could have separate lecture for that. So sampling theorem states like now before going to sampling theorem, there is an obvious question. If we are converting this analog signal into a sampled version of it, like this one, so a prime requirement would be the information should not be lost. Information means let's have some different thing to represent this idea. So information means like we have this signal, okay, and if is a let's say this signal, if it is a fast varying signal, or let's say we are taking the samples only this duration, we take this, took this, we took this, it is a uniform sampling. Okay, so its sampled version, will look like this. So in sampled version domain, it has lost its information or its shape. So if we are going to reconstruct it, it will be like this. So it is totally different from this signal. So obviously we don't want that. What we want through the sampling should be such that the information of the signal should be contained. So we need to take the samples as close as possible so that they contain the information carries by the signal. So now if we represent this sampled version of the signal, it would be like this. So and if we keep going on by this method, so the shape is being more or less is preserved, and if we reconstruct it using some interpolation method, so original signal will be reconstructed with a very minimum of error. So this is our prime aim of the sampling. So sampling theorem provides a mathematical description like what should be the sampling frequency, so that our information presenting or information having in the signal doesn't lost. So that is given by this sampling frequency. So it says like this sampling frequency f of s should be greater than or equal to at least twice to that of the maximum frequency component present in the message signal, where fm is the maximum frequency component in message signal or any incoming signal. For example, suppose if I have a signal consist of, or if I am speaking, so my voice goes up to 20 kilohertz, human speech 20 hertz to 20 kilohertz. So in order like if we are doing a sampling, because we are converting our voice signal from this microphone and it is becoming a digital one and being stored inside the computer, so my information doesn't lost so that sampling frequency should be such that it should be greater than the maximum frequency component present. That means maximum 20 kilohertz. My signal frequency was 20 kilohertz, so maximum sampling frequency which we can have, that should be greater than the 40 kilohertz signal frequency. So that is why if you look at the sound card specification, it samples the signals at 44.1 kilohertz, so that all the information remains saved. So this is the prime requirement for the message for this sampling theorem. Okay, now coming back to this one, once we have this sampled version, sampled signal, while keeping all these things into mind, okay, what is this, and generally it represents like this, x of nt, or more or less x of n, and n is the sample number. Okay, once this sampling is done, now another point is the quantizer. So what exactly quantizer do? Let's have this one, because ultimately right now in the sampling one we can't have this amplitude. Theoretically it could have any possible values, but we can't have that liberty when we are storing inside the computer. So let's say these are the sampled versions, and let's say it contains some value of 1.1 volt, it contains 1.5, it contains 1.9, and it contains 2.0, and so on. Now when we are converting into a digital, we have limited by word length limitation. Word length limitation means how much digital word or digital bits are being used, or we can say how much digital bits are going to be used. That means suppose we are using a 4-bit length. So 4-bit means and obviously within the voltage range of 0 to 5 volt. So 4-bit means we can have these numbers 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, and so on, right? Because we are converting into a digital one. So this 4-bit means between 0 to 5, so it will divide into how many levels? 2 to the power 3 levels. So we can say this 4-bit length is the word, and we are converting into this. So if this represents 0 volt, so what would be the representation of this 001 volt number? That depends like how much step size or how much voltage gap is being there. So ultimately if we have 4-bit, that means we are dividing this entire 0 to 5 volt range, right? 0 to 5 volt range in how many steps? 2 to the power n minus 1 steps, where n is the number of bits used to step a number. So this 5 divided by 2 to the power 8, that means 15. We are decomposing this entire length into 15 small parts. So 15 small parts means if this number is 0, the next would be let's have a quick calculation. 5 divided by 15, it comes out to be 0.33. so there is a gap of 0.33 in each step, so it will be 0.33, then it will be 0.67, then it will be, and so on, and all the information between these will be lost. So similarly if it is a 1.1, so all the information is lost, so this is known as the step size. Now this represents like this 0001 represents 0.33 volt, this represents 0.67 volt, and so on. So what quantizer do? Quantizer converts this any value towards is the maximum nearest value. For say its nearest value will be 0.99, and then it would be, if we multiply 0.33 by 4, 1.32, right? So this 1.1 would be down to, and it will be treated as a 0.99 volt. So that is what we done in quantizer. So ultimately it quantizes, or it rounded off the any value of the discrete number, amplitude of the discrete number, to the nearest value. So that is the simple thing. You can find a lot of literature on that. And then further coder, so Quantizer ultimately represents this value depending on the number of bits used by the coder, and then coder each bits, suppose it is 0.33 volts, so it gives the code according to, like it was the second code, so 0001 for 4 bit, for 0.67 it will give 0010, and so on. So this is the entire process. So in computer these numbers are stored like this, and this represents let's say 1, this represents a 2, another represents a 0. So all the 0 to 5 volt range has been divided into these numbers 0, 1, 2, 3 and up to 15. So this is how this digital number is stored. Now once we have converted into a digital number, another would be like how to we are going to retrieve it back. So that is D to A converter or digital to analog converter. So whatever we are discussing right now, we are discussing just the pure basics of the DSP, how we are coming to digital numbers, and these are must to understand. Digital to analog converter. So what does digital to analog converter do? Digital to analog converter means we have a number in digital 1, 2, 3 and up to 15, and specifically all these are coded into binary like 001 for say 4-bit number, 0010 and 0011 and so on. So digital to analog converter means it is a device which ultimately when we fed a digital number to it, it gives the corresponding analog output to it. So for that there is a formula for analog output, analog value. Formula is equals to V reference, which we used to convert into the analog number, that was 5 volt, into A0 by 2 plus A1 by 2 plus A2 by 2 or 2 to the power 2, a 2 to the power increase, then 8 and then so on. This will be keep on increase, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4 and so on. So let's take in our just our previous example, we use this 5 volt as a reference because this was the maximum value and a 4-bit number. So our number was, let's say, 0010. So corresponding analog value will be V reference 5 into 0 by 2 plus 0 by 4 plus 1 by 8 plus 0. So if we multiply 5 into 5 divided by 8, so it is ultimately 5 divided by 8, that will be coming out to be 0.625. 0.625 volt, right? And similarly it is similar to the previous one voltage, because we are dividing into 5 divided by 15, it is nearly similar to it. So this is how we convert a digital number to analog value when we are giving it towards the real hardware device again. Okay. Okay, so all this was the basics for representation point of view, how to represent. Now coming to the main thing, so digital sequence representation or digital or discrete sequence. So you don't confuse with the digital and discrete now, because many of the books use discrete signal processing, like by Sanjit K. Mitra, computer based approach, and some of the books use digital signal processing. Everything remains the same. So now digital signal representation, or instead of signals in digital we said sequence, digital sequence representation. So it is represented by generally, so x of t was analog domain and we converted into replace t by nt. So generally we used as n of t, or more popularly we use x of n while specifying the numbers. So any x of n, that is a digital sequence, it is stored like 0, 1, 2, 1, minus 3, minus 2, minus 4, and so on. So if nothing is given, it is by default the index number, like n number, goes like this. It is 0 number, 1, 2, 3, 4, 5. If we want to specifically like what is the index number, or it could be we have to write like this, like minus 1, minus 4, 0, 2, 4, 1. So, and we specify like this arrow. So this arrow indicates the 0 is starting from here. So if 0 index is starting here, this index is minus 1, this index is minus 2, this index is 1, 2, and 3. So this is how we represent our digital sequence, and these are known as the indexes, and this is known as the sample value. In graphical domain, we can also represent it like this. So this is x of n. It is 0 at 0. So let's say 0. It is 1. Then 2. The sequence was 1 again. Then minus 2. And then minus 4. So this is 1. This is 2. This is minus 2, and this is minus 4. Similarly, we can also plot the such graph like for this x of n. So these are the representation of this digital sequence in digital domain. Now coming to the moving forward. Now similarly, if we go up to some element basic course, signals and system, and while moving forward in this digital signal processing, we are assuming that you have taken a course like signals and system. That is a very basic course. So or in that course you have been gone through some of the basic signals like unit step signal, unit impulse, and ramp signal. So let's have basic elementary discrete time signals or digital sequences in line with that. So elementary digital sequences. Or generally discrete time sequences. So don't confuse with these two words. First is the unit step sequence, or another unit impulse sequence. So in this unit impulse sequence, this exists only at n equals to 0 and 0 elsewhere. So if we write the representation, it exists 1 when n is equals to 0 and 0 when n is not equals to 0. Similarly, another one is the unit step sequence. So representation of this unit step, mathematical representation, is like this. It is 1 for n is greater than equals to 0 and 0 when n is less than 0, and graphically it could be represented like this. All sequences 1 and this is n. Third could be like unit ramp sequence. So in this unit ramp sequence, this x of n can be write like n when n is greater than to 0 and 0 if n is less than 0. Like this is n and this is x of n. So it will go like this: 0, 1, 2, 3, 4, and so on. This is 1, 2, 3, 4. Similarly, this is 1, 0, 2, 3, 4, 5, and so on. So these are some of the basic sequence. Similarly, there is exponential sequence and other sequences. We will be discussing into the next lecture. So I hope you now comfortable with some of the basic terms being used for DSP, and in our next video we'll talking about the digital frequency and digital sinusoidal signals and so on. A lot of stuff about frequency, that is a very important concept about it. So still that will be the basic. So things to remember from it, like requisite, we can say, required things from your side to go along with this lecture series. You are familiar with the signals and systems subject, because that is the very basic. So similar ideas like time shifting, how to do shifting operation, or there are several operations along with it, like time shifting operation, time multiplication operation, etc. Similarly, you are comfortable with the systems like causality, what are causality, what are memory-less system, what are memory system, and also on. So because in this video we will be talking about linear time invariant system, and we will come to that definition directly, and what we mean by stability and so on. Okay, so quick review. So in this video we just talk about various signals, and then we talk about how to come to the digital sequences from these analog time domain signals. So it was just a brief idea about it and rough idea. So if you go through into the detail, you will be feeling it like a familiar thing, and thing like digital and discrete, throughout the course these two terms used interchangeably, so never confused with them. So that's it for this video. In sub part of this video are MATLAB and Python program for these elementary signals. Okay, so go through that in order to generate these sequences in Python and MATLAB as well. So that's it for this video. Thank you.